For decades, Pluto was little more than a blurry dot in telescopes. We knew it was small, icy, and orbiting on the edge of the solar system, but almost everything else was a mystery. Even its surface features were hidden, and scientists debated whether Pluto was geologically dead or still active. That debate ended in 2015, when NASA's New Horizons spacecraft flew past Pluto and sent back the first close-up images. What New Horizons revealed shocked scientists. Instead of a frozen, lifeless rock, Pluto turned out to be a dynamic world with vast plains of nitrogen ice, mountains as tall as the Rockies, and even signs of active geology. Its thin atmosphere glows with layers of haze, and its surface is shaped by processes no one expected to find so far from the Sun. The flyby changed Pluto from a faint point of light into a complex world with unique features. A giant heart-shaped region, methane-ice spires, possible cryovolcanoes, and winds capable of forming dunes. Each of these discoveries challenged earlier assumptions about what small distant bodies could look like, and even raised new questions about whether Pluto might still have a liquid ocean deep underground. In this video, we're going to break down what NASA really found on Pluto. We'll look at the geology, the atmosphere, the possibility of volcanoes, and we'll even explore some of the most detailed, real images captured during the mission. By the end, you'll see why Pluto went from being just another icy body to one of the most fascinating places in the solar system. When New Horizons approached Pluto in July 2015, at a distance of approximately 5.9 billion kilometers from Earth, no one knew exactly what to expect. The best images we had before then came from the Hubble Space Telescope, which showed Pluto as little more than a fuzzy ball with vague light and dark patches, lacking the resolution to reveal detailed surface features or geological structures. These Hubble images, while groundbreaking for their time, offered only tantalizing hints of Pluto's complexity, fueling anticipation for closer observations. That's why the first close-up photographs from New Horizons became one of the most dramatic moments in planetary science. For the first time in human history, we saw Pluto as a world with sharp features, textures, and a landscape that looked surprisingly complex. The most famous image is the one that revealed the now iconic heart-shaped feature on Pluto's surface, officially named Tombor Regio after Clyde Tombaugh, who discovered Pluto in 1930 by meticulously comparing photographic plates at Lowell Observatory. This single image changed how the public saw Pluto, transforming it from a cold, anonymous body at the edge of the solar system into a world with unique, recognizable, and inviting character. The heart became a symbol of New Horizons' success, but to scientists, it was much more than that. It hinted at geological processes that were still shaping Pluto's surface, even in the distant reaches of space. Zooming in on Tombor Regio, the western lobe of the heart, known as Sputnik Planitia, revealed a vast plain of nitrogen ice with no visible impact craters. The lack of craters is important because it tells us the surface is geologically young, perhaps less than 10 million years old. That might sound old on human timescales, but in planetary science, it's the equivalent of finding fresh paint on a structure that should have been weathered for billions of years. Images showed polygonal patterns across the ice plain, which scientists believe are caused by convection currents in the nitrogen ice. Essentially, the surface is slowly churning as heat escapes from Pluto's interior. Other photos showed mountain ranges that rival some of Earth's. Peaks like Wright Mons and Pickard Mons rise several kilometers high. But instead of being made of rock, they appear to be constructed of solid water ice. On Earth, water ice melts easily, but in Pluto's frigid temperatures, it is as strong as rock. The images of these mountains suggested they might even be ancient cryovolcanoes, volcanoes that erupt not molten rock, but slurries of ice, and possibly ammonia. This idea was reinforced by the appearance of broad summit depressions and fractured terrains around these peaks. If confirmed, Pluto would join the short list of worlds in the solar system with evidence of volcanic activity, and it would be the first known example of such activity so far from the Sun. New Horizons also captured surprising detail in Pluto's atmosphere. As the spacecraft flew past and looked back at Pluto against the Sun, it revealed layers of bluish haze extending hundreds of kilometers above the surface. The images showed more than a dozen distinct layers of haze, giving Pluto's sky a layered, almost stratified look. This haze is likely produced by ultraviolet light from the sun breaking apart methane in the upper atmosphere, which then recombines into more complex hydrocarbons that settle downward. Some of these compounds likely coat Pluto's surface, giving it its reddish-brown color in certain regions. The images provided hard evidence that Pluto's thin atmosphere is not static. It actively interacts with sunlight and with the surface below. One of the more unexpected findings came from images of dune-like features along the edge of Sputnik Planitia. Dunes usually require a substantial atmosphere and winds to form, which scientists did not expect on Pluto. But New Horizons cameras picked out ridges and wave-like patterns that strongly resembled sand dunes on Earth. Instead of sand, these dunes are thought to be made of methane ice grains, pushed into place by winds blowing across the icy plains. That discovery alone proved that even Pluto's thin atmosphere is capable of shaping the surface in ways that parallel processes on Earth. Another stunning set of images revealed bladed terrain near Pluto's equator, consisting of long, jagged ridges that may stretch hundreds of meters into the sky. These features are thought to form when methane-ice sublimates, turning directly from solid into gas, leaving behind sharp spires. Similar processes create penitentes, jagged snow formations found in Earth's high-altitude deserts. But on Pluto, they occur on a scale far beyond what we see on Earth, adding another layer of mystery to how its climate and surface interact. New Horizons also captured views of Pluto's smaller moons, including Charon, which revealed its own surprising geology. Pluto, with a diameter of approximately 2,377 kilometers, is smaller than Earth's moon. Its largest moon, Charon, measures about 1,214 kilometers in diameter, making it roughly half Pluto's size. The smaller moons, Styx, Nix, Kerberos, and Hydra, are far tinier, irregularly shaped bodies. Despite their size differences, each moon added to the mission's revelations. The main focus, however, remained Pluto itself. Each image peeled back another layer of assumptions built over decades of distant observation. Instead of an inert, frozen rock, Pluto appeared as a dynamic world of ongoing change, with flowing ices, hazy skies, windswept plains, and possible volcanic eruptions frozen in time. The sheer amount of detail in these images changed Pluto's reputation forever. What once seemed like a distant, icy footnote in the solar system became a dynamic world worthy of study in its own right. And for planetary scientists, the pictures were not just stunning. They were a call to revisit questions about how such a small body could remain active billions of years after its formation. Pluto's surface shows a diversity of terrains shaped by processes that go beyond simple impact cratering. Some regions are heavily cratered, representing ancient surfaces that date back billions of years, while others look comparatively fresh, resurfaced by internal or atmospheric activity. This variety makes Pluto a geological mosaic rather than a uniform icy body. One of the clearest signs of activity comes from Pluto's mountain ranges. Peaks such as Tenzing Montes and Hillary Montes rise several kilometers above the surrounding plains. These mountains are composed mainly of water ice, which at Pluto's frigid temperatures is as strong as rock. Their sharp, rugged outlines indicate that they are relatively young features, not yet smoothed or erased by erosion processes. The presence of such towering mountains shows that Pluto's crust is strong and capable of supporting large, stable structures. Planetary scientists, using data from New Horizons, revealed that Pluto's surface is crossed by fractures and fault systems that extend for hundreds of kilometers. These features suggest that Pluto's crust has been stretched and broken, likely due to internal changes, such as the slow freezing of a subsurface ocean. As liquid water turns to ice, it expands, exerting pressure on the crust and creating wide rift valleys and troughs. The scale of these fractures indicates that Pluto's interior has evolved significantly over time, reshaping the outer layers in the process. Another striking aspect, uncovered through New Horizons data, is Pluto's color diversity. Spectral measurements identified deposits of methane and carbon monoxide ice in many regions. along with widespread reddish material known as tholins. Planetary scientists determined that tholins form when ultraviolet radiation breaks apart methane molecules in the atmosphere, producing complex organic compounds that settle on the surface. These compounds are responsible for Pluto's reddish hues, particularly noticeable in its equatorial regions. By contrast, areas rich in nitrogen ice appear much brighter, giving Pluto a patchwork of light and dark zones that trace where different ices accumulate and evolve. Pluto's surface also shows evidence of erosional and sublimation-driven processes. In certain regions, clusters of pits and depressions appear where nitrogen or methane ice has vaporized directly into the atmosphere. This process of sublimation carves shallow basins and creates an ever-changing surface. Such features demonstrate that even without liquid water on the surface, Pluto's ices can behave in dynamic ways, eroding and reshaping the terrain over geologic timescales. The combination of mountains, fractures, color variations, and volatile-driven pits makes Pluto's geology unusually complex for a body of its size. Each feature reveals how different types of ice, water, methane, nitrogen, and carbon monoxide, behave like rock, sediment, and soil do on Earth, only under much colder conditions. Rather than being static, Pluto's surface is a record of ongoing interactions between its interior, atmosphere, and the space environment around it. One of the more unusual discoveries from New Horizons images was a set of sharp ridges running along parts of Pluto's equator. This landscape is called bladed terrain because of its resemblance to enormous knife-like formations. Individual ridges can reach hundreds of meters high, forming vast fields of jagged spikes that stretch for miles. Analysis of spectral data suggests that these structures are made primarily of methane ice. On Earth, a similar process creates penitentiae, small spiky snow formations in high-altitude regions such as the Andes. In those environments, sunlight sublimates snow unevenly, carving narrow troughs and leaving behind tall blades. On Pluto, the same process seems to occur on a much larger scale, but with methane ice instead of snow. Thin atmosphere and extreme cold slow the sublimation process, allowing features to grow taller and more exaggerated than anything seen on Earth. The presence of bladed terrain raises questions about how Pluto's climate has varied over time. Pluto follows a highly elliptical orbit around the Sun, taking 248 years to complete one revolution. Over these long seasons, the intensity of sunlight and the distribution of ices across its surface change significantly. The bladed formations may preserve a record of past climate cycles, with their growth and erosion linked to changing patterns of solar heating. Studying them helps scientists reconstruct not just Pluto's present surface, but also its climatic history over millions of years. Pluto is not classified as a planet, but as a dwarf planet, according to the International Astronomical Union, IAU, definition established in 2006. The IAU defines a planet as a celestial body that orbits the Sun, is spherical or nearly spherical, and has cleared its orbit of other debris. Pluto meets the first two criteria but fails the third, as it resides in the Kuiper Belt, a region populated with other objects, and thus does not clear its orbit. However, this classification is controversial. Some scientists, like Alan Stern, the principal investigator of NASA's New Horizons mission, argue that Pluto should be considered a planet due to its geological complexity, including mountains, valleys, and a thin atmosphere, as revealed by New Horizons. They contend the IAU's orbit clearing criterion is flawed for objects in the Kuiper Belt, where clearing orbits is less feasible due to the region's high density of objects. Public sentiment often leans toward calling Pluto a planet for historical and cultural reasons, though these lack scientific weight. Despite the debate, the IAU's definition stands, so Pluto remains a dwarf planet, alongside bodies like Eris and Ceres. These geological complexities, observed by New Horizons, underscore why the debate over Pluto's status persists, as its dynamic surface rivals that of larger planetary bodies. In the western part of Sputnik Planitia, researchers identified dune fields composed not of sand, but of methane ice particles. Despite Pluto's thin atmosphere, winds strong enough to move grains appear to exist, especially along the boundaries of large nitrogen ice plains. The dunes resemble terrestrial ones in shape, forming parallel ridges that migrate slowly over time. This discovery demonstrates that even a tenuous atmosphere can drive geological processes when conditions are right. Other regions display pitted landscapes, shallow depressions that likely result from the sublimation of nitrogen ice. These pits may grow and merge over time, reshaping entire plains. Nearby, networks of troughs and valleys cut across the surface, some extending hundreds of kilometers. These tectonic features suggest that Pluto's crust has experienced stress, possibly from the gradual freezing and expansion of an interior ocean. Together, these exotic landscapes show that Pluto's surface is not shaped by one dominant process, but by a complex interplay of sublimation, wind, tectonics, and climate variation. Each type of terrain provides a different piece of evidence about how energy and material move around the planet. Methane blades record long-term climate cycles. Dunes capture the influence of winds in a thin atmosphere. Pitted plains reflect volatile exchange between surface and sky. And tectonic valleys reveal stresses from deep within Pluto's interior. For planetary science, these findings matter because they broaden the range of known geological processes at work in the outer solar system. Worlds like Mars and Titan already showed that wind and atmosphere could sculpt landscapes. Pluto now adds its own examples, showing that even on small, cold, distant bodies, similar processes operate under very different conditions. Among the most debated features on Pluto are the vast dome-like mountains that suggest the presence of cryovolcanoes. Unlike terrestrial volcanoes, which erupt molten rock, cryovolcanoes release mixtures of water, ammonia, methane, or other volatiles that behave like lava under frigid outer solar system conditions. The New Horizons spacecraft imaged two particularly massive candidates, Right Mons and Picard Mons. Right Mons rises nearly 4 kilometers above the surrounding plains and stretches over 150 kilometers across. Its summit contains a large depression, several tens of kilometers wide, resembling a caldera. Picard Mons, even taller, is comparable in scale. What makes these mountains unusual is their structure. Broad bases, steep flanks, and central depressions consistent with volcanic constructs. Unlike impact craters, which scatter debris outward, these depressions appear to have formed from collapse after material erupted and drained away beneath. The idea of volcanism on Pluto is surprising because it requires an internal heat source. For a small body located nearly 6 billion kilometers from the Sun, conventional models suggested that internal activity should have ceased long ago. Yet features like Right Mons imply otherwise. One possible explanation is radiogenic heating, the decay of radioactive isotopes such as uranium, thorium, and potassium in Pluto's rocky core. Even in small amounts, this decay produces steady heat over billions of years. Another possibility involves a subsurface ocean. If Pluto contains a liquid layer of water mixed with ammonia beneath its icy crust, that ocean could remain stable due to antifreeze effects. As the ocean slowly freezes, it would expand, fracturing the crust and potentially forcing slushy mixtures upward through vents, creating cryovolcanic domes. Support for this comes from Pluto's widespread tectonic features, which look consistent with crustal expansion over time. The surface composition of suspected cryovolcanoes strengthens the case. Data from New Horizons instruments show water ice signatures concentrated in these regions. Unlike Sputnik Planitia, dominated by volatile nitrogen and methane ices, the cryovolcanic constructs appear rich in water ice. This distinction suggests that material from deeper within Pluto has been brought to the surface, just as volcanism on Earth exposes mantle-derived material. If cryovolcanism is indeed active or recent on Pluto, the implications are far-reaching. It would mean that Pluto has not fully cooled and that its interior remains thermally dynamic. More importantly, it raises questions about habitability. Liquid water, combined with energy sources and organic molecules, provides some of the essential ingredients for life. While Pluto's surface is far too cold and hostile, a stable subsurface ocean insulated beneath kilometers of ice could theoretically support microbial ecosystems, similar to hypotheses about Europa or Enceladus. Even if life is unlikely, cryovolcanism still transforms how scientists think about small icy worlds. Instead of being inert leftovers of planet formation, bodies like Pluto may be chemically and geologically active long after their birth. That activity reshapes their surfaces, circulates materials between interior and exterior, and produces environments far more complex than expected. Comparisons help put this into perspective. Neptune's moon Triton, roughly similar in size to Pluto, also shows evidence of cryovolcanism, including geysers observed by Voyager 2 in 1989. Saturn's moon Enceladus currently vents plumes of water vapor and ice into space. Even Ceres, a dwarf planet in the asteroid belt, has features that may result from icy volcanism. Pluto now fits into this growing category of icy worlds where interior activity persists against the odds. The difficulty is confirming how recently Pluto's cryovolcanoes were active. New Horizons had only a brief flyby, meaning it could not monitor changes over time. The lack of superimposed craters on some features hints that eruptions may have occurred relatively recently. But without a long-term mission, it is impossible to know if activity continues today. Future orbiters or landers would be required to detect thermal anomalies, venting, or other clear evidence of ongoing cryovolcanism. In planetary science, Pluto's suspected volcanoes serve as reminders that geological activity is not limited to Earth-like conditions. Even in the coldest regions of the solar system, energy can accumulate, pressure can build, and eruptions can reshape entire landscapes. The mountains of Wright Mons and Picard Mons are monuments to that principle, standing as frozen records of internal processes still at work beneath Pluto's icy surface. What these discoveries showed is that Pluto is not an exception, but a representative of a whole category of worlds waiting to be explored. The Kuiper Belt is filled with objects similar in size and composition, yet Pluto is the only one we have seen up close. If one dwarf planet can host active geology, seasonal atmospheres, and possible oceans, then the diversity of the outer solar system is far greater than once imagined. Pluto is no longer a curiosity at the edge. It is a case study in planetary complexity. The open questions are as important as the discoveries. Does Pluto still have an internal ocean? Are its volcanoes dormant or active? Will its atmosphere collapse at aphelion? How does its unseen hemisphere compare to the one New Horizons revealed? Each of these questions points to the need for follow-up exploration. The brief flyby was only the beginning. It showed what is possible, but left the details unresolved. That is why many scientists argue for a Pluto orbiter mission. Unlike the flyby, an orbiter could spend years mapping the entire surface, tracking changes in the atmosphere, and searching for signs of ongoing geological activity. Instruments capable of probing Pluto's gravity field could confirm the presence of a subsurface ocean. Infrared sensors could detect heat anomalies from cryovolcanoes. Long-term monitoring could reveal seasonal cycles in real time. Such a mission would not only answer Pluto's mysteries, but also provide a template for understanding other Kuiper Belt objects. Exploring Pluto also has value beyond planetary science. It reminds us that the solar system is not a set of neat categories, but a continuum of worlds shaped by common processes under different conditions. It forces us to expand our definitions of habitability, to think about water and chemistry not just on Earth-like planets, but on icy bodies far from the Sun. And it reinforces the point that exploration often overturns expectations. What was once assumed to be a frozen relic is now seen as a place of activity and possibility. Looking ahead, Pluto's role is twofold. It is a gateway to the Kuiper Belt, the first of its kind to be explored in detail. And it is a symbol of planetary diversity, demonstrating that even the smallest and most distant worlds can be surprisingly complex. Future missions will likely build on this legacy, not just by returning to Pluto, but by extending exploration deeper into the Kuiper Belt and beyond. Pluto's story is unfinished. The first chapter has been written by New Horizons, but the next chapter will come only when humanity returns with new spacecraft and new tools. Until then, Pluto stands as a reminder of how much remains unknown, and how much more there is to discover in the vast frontier beyond Neptune.